Okay, are you ready to begin, Hülya?
Yes.
Okay, we're pleased to have Hülya Argüz, who's going to tell us about enumerating log maps via wall crossing. Thank you.
Thank you very much for the invitation. Great pleasure. Today I'm going to talk about joint work with Mark-Ross. The plan of my talk is as follows. I'll tell you a little bit about local Calabi-Yau pairs and then of log Gromov Witten and punctured log Gromov Witten invariants of Abramovich-Chen-Gross-Siebert. I see that then Abramovich is here. I'm very, very happy about that. And then I will tell about the two-dimensional case on how to compute log Gromov Witten invariants algorithmically following work of Gross-Siebert on the tropical vertex, and how it fits into the mirror symmetry program of Gross-Siebert. And then I will tell you about a higher dimensional case and what we did here with Mark-Ross, which is an algorithm on how to compute punctured log Gromov Witten invariants algorithmically. All right, log Calabi-Yau pairs. A log Calabi-Yau pair is given by an n-dimensional smooth projective variety X over C and a reduced simple normal crossing divisor D and X, which is anti-canonical. And we denote by Di the irreducible components of D, and we assume that Xt is maximally degenerate, which means that we assume there's some index set J with some components Dj having non-empty intersection and such that the intersection is zero-dimensional. It in particular imposes that D is not smooth, and it implies in particular that if once we talk about tropicalizations, the tropical picture has the correct dimension. And as an example of a log Calabi-Yau pair, we can consider smooth projective toric varieties X sub sigma with 1 sigma, where D sigma is the toric boundary divisor. And a more interesting example is if we consider blow-ups of toric varieties at general hypersurfaces on the toric boundary. So if you take H, H1 to HS, and the toric boundary divisor in a toric variety, and if we blow them up, we obtain a maximally degenerate log Calabi-Yau pair. And this is more interesting from the mirror symmetry perspective because a toric variety contains no zero massive index disks, whereas these blow-ups do contain, and they do have non-trivial mirrors. Okay, so now I'd like to tell you a little bit about log Gromov Witten theory for log Calabi-Yau pairs. Before switching to log, let me just remind Gromov Witten theory. Apologies, everyone here, I believe, might know all this, just to set up the notation. When you say n-marked genus G stable maps to X of class beta, you consider the moduli space, which we denote by m bar Gn, and there are natural evaluation maps from this moduli space to X. And when we fix, in addition, some cohomology classes, we define the Gromov Witten invariants associated to this data by taking the pullback of these cohomology classes under these evaluation maps and integrating over the virtual fundamental class. The two main techniques to compute Gromov Witten invariants are given by localization and degeneration techniques, the latter using relative Gromov Witten theory. So what I will talk about today is essentially an expansion of relative Gromov Witten theory. So in relative Gromov Witten theory, in addition to the data to define Gromov Witten invariants of X for each marked point, we fix a non-negative integer mi, and we define the relative Gromov and the divisor d in X, and we define the relative Gromov Witten invariants as counts of stable maps of class beta genus G such that they intersect D, the divisor D, with contact order mi at the ith marked point. Okay, and why is relative Gromov Witten theory interesting? There are several reasons. One of them is that there is the Degeneration Formula. One of the main tools to compute Gromov Witten invariants is telling that you can recover actually absolute Gromov Witten invariants of a space X in terms of relative Gromov Witten invariants if you degenerate X into two components, X1 and X2, meeting along a divisor D. You can recover absolute Gromov Witten invariants in terms of formula using relative Gromov Witten invariants of X1 relative to D and X2 relative to D. And this belongs to Juni, who in the algebra geometric setup first defined relative Gromov Witten invariants in the case where you have a smooth divisor D. And his setup requires expansions of the target. So the idea is this: if you naively look at relative maps with given tangency order with D, and if you want to compactify this modular space of such maps, at some point such maps might have components falling into the divisor at some limit. And if you naively take the compactification using such curves which fall into the divisor, things don't work so well. You cannot construct a nice virtual fundamental class, and the solution proposed by Juni was to construct maps to find the moduli space by compactifying with maps which live in bubbles. So he constructed these bubbles, which are P1 bundles over D, and you're considering curves which are admissible, which means there's no component mapping into D and which live on these P1 bundles, as in the right upper corner picture. If you contract the P1 bundle, you will obtain a curve which lives in D. And the solution proposed by Abramovich-Chen-Gross-Siebert in a more general setup where you can consider not smooth but log-smooth divisors, which are typically divisors with singularities. For instance, you can have normal crossing singularities, is based on not modifying the target, but looking at maps where you do everything with some sheaves of monoids with particular sheaves called log structures, and to encode all the data you need in terms of these sheaves of monoids. So if you want to encode the data of a contact order at a marked point P, mapping to f of P with some given contact order, you can say, okay, if the contact order is 5, I'm going to encode this data by defining a map which maps 1 to 5. And the way to define such maps is looking at some sheaves, which I denote by m bar, which I will define. They are called Gauss sheaves. And these sheaves are the discrete part of the log structure we're going to define. And this has the advantage that it works without modifying the target, and it works for more general divisors. Okay, what are these log structures? A log structure on a scheme X is a sheaf of monoids together with a map to the structure sheaf, inducing an isomorphism on the invertible elements of the structure sheaf. And a log scheme is a scheme with a log structure. The Gauss sheaf of a log scheme is the sheaf of monoids, which you forget about the invertible elements. You quotient out by the isomorphic copy of the invertible elements. Before defining the tropicalization, let me just give an example of a log structure we will be using. So in this setup of Calabi-Yau varieties, there is a natural log structure we consider. When you have a divisor D in X, you consider the complement X minus D included in X by inclusion map J. And then you can define your sheaf as the sheaf of regular functions which are invertible away from D. And for instance, on A1, if you take the divisor given by 0, this sheaf will have Stoic at 0 given by invertible functions times t to n if t is the coordinate on A1. And if you forget about invertible functions, you just have t to n, and then you can define your isomorphism. Your Gauss sheaf will just have Stoic n if you define the isomorphism mapping t to n where n is a natural number. So this is the discrete part of the log structure given by Gauss sheaves, which we use to define the contact data that I mentioned. And the nice thing about log structures is they behave well under pullback. So whenever you have a subscheme, you can pull back your log structure to your subscheme. So if you just look at the point 0 in A1, you can define a log structure obtained by the pullback by the divisorial log structure. It's given by taking your sheaf of monoids as C star direct sum n, and defining the map alpha to your structure sheaf, mapping a pair xn to either x or 0, depending if n is 0 or not. So this is a particular log structure on the log point. There are many log structures you can define. You can also define the trivial log structure, in which case you would take mx just c star, and your map alpha will be the inclusion. So if we go back to the previous slides, whenever you have a log structure in this discrete data given by the Gauss sheaf, you can define the tropicalization of your log scheme just in terms of m bars. So you define it as a Kohn complex given by unions of Kohns defined by homs of m bars to r greater or equal 0. And use some identifications. So for instance, in the case of A1, you just have the natural numbers from n to r greater or equal 0 is just r greater or equal 0. So your tropicalization is just the same as the toric fan of A1. And if you would have P1, you would have two natural numbers corresponding to the 2 points forming the canonical divisor, and I would identify these two r greater or equal 0s. So in general, if you have a toric array with the divisorial log structure given by the toric boundary divisor, you obtain the toric fan as your tropicalization. What are log maps? Log map, if you take the log point and the log scheme over the log point, in applications, this log point will be either the trivial point or the standard log point, depending on which setup you're working. And a stable log map is given by a commutative diagram mapping C to X, where X is over a scheme over S, and everything is endowed with a log structure. And the subtlety is to define where the source occurs, what the point, so C has a map to WMW, and the subtlety is to define the log point. And this, I will talk about this in a moment. So you require C to be log smooth over some log point. And I will tell the construction of W in a moment. So the idea naively is in the setup of Chumni, you need to decide, you need to understand, analyze a lot of data to understand how many bubbles you need. You need finitely many bubbles, and this depends on various data, such as how many components of your curve you have, which map to the D, what are the contact orders, and so on and so on. And all this data is going into the information of this W here, where our domain is log smooth over. Log smooth means locally the map is induced by toric monoids, like maps between toric monoids. Okay, to define W, I need to tell you what a combinatorial type of a map is. The combinatorial type of a map C to X consists of the data of the dual intersection graph of the domain C, the genus function associated to the vertices, and the map mapping the dual intersection graph to the tropical X, which is in toric situations the fan. In addition, you need the contact data, which I mentioned. And once you have the combinatorial type, once you know the combinatorial type, you can define a monoid, and this is going to define the W, which I was mentioning your curve is supposed to be log smooth over. So you define your monoid Q by first defining its dual. The dual of Q is defined by taking some sum of monoids. You need as many copies of N as you have nodes. And for every generic component, you need to take some sum with the dual of the Gauss sheaf at the stalk of this generic component. This way you can define a monoid. And then you define your W such that W is obtained from this monoid you defined out of the combinatorial type. So given a stable map, one can show that there is a canonical map from this monoid Q to the Gauss sheaf of W, and where Q is the basic monoid defined by the combinatorial type, and by definition, a stable map is said to be basic if the natural map of monoids Q to M bar W is an isomorphism. And the theorem of Abramovich-Chen-Gross-Siebert is saying that the modular space of basic stable log maps is a Deligne-Mumford stack. And for every G and genus and homology class and contact data U, another theorem, this is a Deligne-Mumford stack, and in nice cases, this modular space admits a virtual fundamental class, so you can do enumeration. And recently, Abramovich-Chen-Gross-Siebert, on their paper on arXiv this year, expanded the theory of log maps. They considered punctured log maps where they are allowing negative tangency orders by modifying the sheaves of monoids which record the contact data. So your contact data is no more an image with natural numbers, but you modify these sheaves I was talking at the very beginning, which record contact data so that you have a map to integers, and this means you allow negative tangency orders. And in punctured log Gromov Witten theory, they prove that if X is proper log smooth, the modular space of punctured log maps of given contact data is a proper Deligne-Mumford stack, and in nice cases you can again construct a nice virtual fundamental class. And today I'm going to tell you more concretely the problem we have with these punctured maps and how to solve this problem. So we want to compute log or punctured log maps, and in dimension 2, an algorithm to compute log maps without punctures was provided by Gross-Siebert in the tropical vertex paper. And this is based on wall crossing and tropical geometry, and with Mark we wrote a paper on the higher dimension tropical vertex, which explains how to compute punctured log invariants out of wall crossing. So I'm very happy Pierik is also here, who explained already wall crossing and how it agrees with the stability wall crossing. It is the same wall crossing I'm going to talk about. Before passing to wall crossing, the last thing I want to mention is, as we will use a lot of tropical geometry, the wall crossing is going to occur in the tropical Calabi-Yau. The tropical Calabi-Yau is just defined. You can use the definition I just said by taking the Kohn complex defined by Holmes from the stalks of ghost sheaves of R greater or equals 0. If you apply this definition, you will see that you will end up with the dual intersection complex of the Calabi-Yau defined purely in terms of the intersection data of D. What I mean here, for instance, if you have, as in the picture in the right-hand side, dp7, which is a toric variety blown up, obtained by blowing up P2 at 2 points, the tropicalization is just the toric fan of dp7 that I drew on the right-hand corner. And if in addition you blow up 2 more points, which are non-toric, which are not fixed under the torus action, your tropicalization, so I drew in small the momentum cone picture of dp7 and in small the almost toric base diagram of dp5, which is obtained by dp7 plus blowing up 2 non-toric points. So it admits a fibration where you have two of your fibers are pinched tori, are nodal elliptic curves, and if you consider the dual of this almost toric base diagram, you obtain 2 singularities, focus singularities in the fan picture. So it looks very similar to the toric fan of dp7. Apart from, you have this integral affine structure with singularities, which means you identify the red regions, you identify the edges of red regions. And why is this happening? If you look at how dp5 is obtained, if you blow up, if you take a configuration of 6 lines, 2 parallel like this and 2 like this, and if you blow up 4 points, you end up with 10 minus 1 curves, 6 from the strict transform of the 6 lines and 4 exceptional divisors, and 5 of them are formed by strict transforms of the boundary of dp7, and each of them is a -1 curve. So if you want to do like a general idea of toric geometry, if you want to build a fan where everything is having self-intersection -1, you start with this on the picture on the left corner. You start with this first and second these, and you want this to be -1, you add this here. You want this to be -1, you need to add this here. You want this curve to be -1, you need to add this here. You know how to compute self-intersection of divisors. If you want this to be -1, so it's, I mean, the way we compute self-intersection, if this is k times the sum of the neighboring divisors, then the self-intersection is -k. So you need it to be -1, you need to have something here, but you don't have something here, so you're saying I'm just gonna identify this first thing with other things, so you put a singularity there. So you have a singularity at the origin, an integral affine singularity as the tropicalization of dp5. This left-hand side picture is how the tropicalization of a Calabi-Yau is defined in Gross-King Q. And you can push the singularity away. There is something called reduction to the Gross-Siebert locus. We don't want singularities at the zero-dimensional strata because we cannot build mirrors if they are there. So you can define an isomorphic integral affine manifold where the singularity at origin is pushed a little bit away into two singularities at these rays. And that's the reduction to the Gross-Siebert locus of the tropicalization, where all scattering and everything is happening and telling you what the mirror is. So in this picture, you see three diagrams where in one there's a singularity at origin, which is the Gross-Seq and Q setup, and the second, the Gross-Siebert setup, where you have singularities away, and in the third, the singularities that are infinity. So the idea is to understand the relationship between these three diagrams to understand mirror symmetry, essentially. So in the tropical vertex, the setup of the tropical vertex, they consider scattering without any singularity and purely in the toric setup. So the setup is as follows. Assume you have a local Calabi-Yau pair obtained by a blow-up of a toric variety x sigma. And you denote by d rho I the divisor corresponding to rho I with primitive ray rho I with primitive generator mi. And assume the map nu, which you blow up to obtain x, is a blow up where you blow up along general hypersurfaces hi's. And then you can, out of this data of the toric surface, together with the data where you will blow up to obtain your local Calabi-Yau, you can define a scattering diagram on the toric fan of this toric surface as follows. So for every ray corresponding to the divisor d rho I functions that Eric also mentioned in his talk yesterday, and they're of the form 1 plus tijz to mi. So for instance, in this example of dp7 and dp5, remember we obtained dp5 by blowing up dp7 at two non-toric points corresponding to two divisors, two components of the anti-canonical divisor, and what I do is I just impose a ball crossing function 1 plus t1x on one of the rays and 1 plus t2y on the other ray. So Pierre already yesterday talked about consistent scattering diagrams. If you do this, if you just impose these functions 1 plus tix and on the rays, where you will do something non-trivial, where you will blow up, this is the initial scattering diagram, and this is not going to be consistent. But there's a nice algorithm defined by Convergent in dimension 2, saying that you can just add more and more and more walls to your scattering diagram, and you can associate to these walls some ball crossing functions and turn your scattering diagram into a consistent one. And a consistent scattering diagram is the one in which you ensure that if you go around the origin and take the composition of all wall crossing automorphisms, you end up with identity. So if you start with these two things, two walls, you need to continue with this, and also at this wall to ensure that you have a consistent scattering diagram. And the computation is not terribly difficult. It's explained in the tropical vertex paper in the simple case. So if you check, you start with x on one side. I wrote all the wall crossing automorphisms. If you cross the wall below, x goes to x times 1 plus t2y, because you cross the wall with that wall crossing function, and then you continue crossing all the walls, and you want to end up, if you make a round, you want to come back to x at the end of the day if you make a loop around origin. All right. So what is the main result of the tropical vertex paper is this. If you fix points x1 onto x1L in the simple situation I'm just drawing the case of P2, and D1 and 1 divisor and x2 to x2L2 in D2, and if you take partitions given by non-negative integers P11 to P1L1 and P21 to P2L2, and if you define big P as the sum of these non-negative integers, and you take partitions satisfying some balancing conditions such that absolute P1, the sum times m1. M1 is the direction of the ray corresponding to d1. Plus p2 m2 is equal to w out times m out, where m out is the direction of the outgoing ray, so of the outgoing thing, where w out is a non-negative integer. And if you fix this data and you define class beta in H2 of your toric variety such that beta times d-ρ1 is p1 and beta times d-ρ2 is p2, the sum of these non-negative integers I fix. And in addition, you consider the class beta tilde, which is now a class in the blow-up in the local Calabi-Yau variety X, where you obtain by blowing up all these points x1, 1, x1, L1 to x2, 1, x2, L2. If you define your class beta by taking the pullback of beta minus Pij times the exceptional curves, and if you let n, m1, m2, p1, p2 be the log invariants of the local Calabi-Yau variety obtained by accounts of log maps, which intersect the exceptional curves over x11 with p11 and the exceptional curve over xij with order pij, and which intersects the divisor, the outgoing divisor with contact or the w out. If you look at such log maps, Grossmann-Siebert showed that the considered Solomon scattering algorithm carries an enumerative meaning, and that the walls, the attached functions to the walls you're adding to complete your initial scattering diagram to a consistent one are of a particular form. The coefficients are given exactly by these log Gromov Witten invariants of the blown up toric variety of your local Calabi-Yau variety. And based on this observation on the tropical vertex cross-secking, you define the canonical scattering diagram by looking exactly at this problem that was solved by Grossmann-Siebert, was understood how it fits to scattering. So the problem is if you fix curve class beta in H2x, and if you fix a cone in your tropical fan picture, and if you fix vector v, which is ami plus b mi plus 1, where a, b are non-negative integers, mi and mi plus 1 are the generators of a race of generating a cone in dimension 2. And then you want to understand the number of genius zero log curves in X of class beta, which intersect D at a single point with multiplicity AB. So you want these curves to intersect D at a single point. If you're on a ray, if either A or B is 0, you will be on a ray. So you will just intersect the divisor, one component of your divisor at a single point. If AB is in the interior, you will intersect, because you intersect your boundary at a single point, you will intersect the intersection of two components. And in this particular example of DP5, you don't have such curves where you go to the singular parts. All your exceptional curves that I mentioned, you have L-1 curves, 5 formed by the strict transforms of the boundary components, and you have 5 other -1 curves. They all intersect the boundary components at one point generically, and the picture on the right illustrates them in the almost toric-based diagram. So you can imagine there's a sphere over these curves I drew as E1, and over each point on the curve you have a circle using the conormal bundle construction. When you go to boundary, the circle gets contracted. When you go into the singularity, the circle gets contracted. So the tropical picture for these curves is just you have one vertex corresponding to the fact that you have one irreducible component and one marked point, so one ray. So you have these 5 tropical curves and DP5. And using this data, these exceptional curves, we're gonna build the canonical scattering diagram. So the canonical scattering diagram is built as follows: for every sigma, a cone in your intersection, a tangent vector to sigma, you let NV beta, so you look at genus 0 log Gromov Witten invariants of class beta intersecting a single point with contact order V, and you let NV beta this invariant, and for every ray, you include a wall with attached wall crossing automorphism given in terms of the log Gromov Witten invariant. And this is the example of the canonical scattering diagram for DP5. I drew at the left-hand side. So you attach to each of these 5 rays where there's a singularity at the origin, 1 plus EI inverse C to EI, where EIs are the exceptional curves I was mentioning, which you can view as these are the tropicalizations of EIs. Why is this important? I will just tell in a slide why canonical scattering is interesting. When you have this data, you can just build a homogeneous coordinate ring of a mirror family to DP5 minus the anticanonical minus the divisor. And how do you do that? So the crucial step is to push the singularity away, reduction to the Gross-Siebert locus. And when you push the singularity away, your wall 1 plus E1 inverse C to E1, your wall divides into 2 walls. On this side, you have 1 plus E1 inverse C to E1, on the other 1 plus C1, C to minus E1. Due to consistency, and then a final ingredient you need is to assign a piecewise linear function on this span. The kinks of the PL function are given by di's on each race, but in the regions between the origin and the singularity by di plus ei's, the kinks change on these regions, and everything is, the whole mirror is going to be determined with the part around the origin. So in particular, if I just drew the part around the origin here again together with the kinks, to understand the mirror, you just look at the wall crossing automorphisms around the origin. And the idea is you can formulate it purely combinatorially by looking at counts of broken lines which are tropical analogs of mass index 2 disks. And I will not spend a lot of time here, but the idea is if you're away from the singularity, your broken lines will always converge away because broken lines bend in the direction of the wall. So you don't care about what happens away, so you care about what happens around the origin essentially. And because I have 12 minutes remaining, I will skip the combinatorics of how it goes. I will just recap that once you have the scattering diagram of the tropical vertex, you can just construct a canonical scattering diagram by changing the Tij variables to Eij variables. And this is intrinsic in GHK, and in all dimensions, what we do with Mark is to define a scattering diagram associated to the toric model of a Calabi-Yau variety, which is a higher dimensional toric scattering diagram. And we show that you can define a higher dimensional canonical scattering diagram, and these two determine each other. And in particular, we show that by doing this, we can algorithmically compute low Gromov Witten invariants. I think I have, how much time do I have?
You have 10 minutes, including questions.
Perfect. So I will just tell how we define the toric scattering diagram. So in dimension 2, look at P3, 2 lines, R1 and R2 in P3. So how do we define the toric scattering diagram is as this. We take the tropical, so assume that our local Calabi-Yau is the local Calabi-Yau variety obtained by blowing up 2 lines, R1 and R2 in P3, such that R1 lives in one P2 boundary component, R2 lives in the other. How do you define the toric scattering diagram? We define our initial walls first by taking the tropicalizations of these lines, R1 and R2. We take these tropical lines and we move them all along the rays corresponding to the divisor where the lines live at, and these are forming our initial walls. And the step functions, we assign 1 plus T1x and 1 plus T2y, similar to the case of the toric scattering diagram defined by Gross-Siebert and Siebert. And we do define in higher dimensions an algorithm which tells you the generalization of conceived Cyberman in higher dimensions, how to complete this to a consistent scattering diagram. So we have now higher dimensional walls, they meet along what we call joints, one-dimensional rays in this case in 3D, And you need to check around each joint. If you take loops around joints, each walls you cross, you take the composition of all crossing automorphisms, you get identity. So around each joint there happens wall crossing. And in this case, in the P3 case, which is starting with the two, starting with these initial walls, so which we call widgets, which are obtained by moving along the tropical lines that we blow up along the rays, we end up the complete consistent scattering diagram has this walls that I wrote here in this table. But the scattering algorithm was very complicated. It never terminated. This is just, so the scattering algorithm included infinitely many walls. The algorithm tells on two walls cross how to add another wall with a monomial of the form 1 plus something. And we had infinitely many walls, and we take the limits, they converged to 1 plus t2y plus t1, t2, xy, for instance. This is the convergent scattering diagram where I cancelled infinitely many walls by what they converged to. And when I do analyze how the relationship between the toric scattering diagram defined by Gross-Siebert and the canonical scattering diagram, when I do the analysis in higher dimensions, it requires analyzing what kind of Kerr classes you replace your Tij variables with. And I obtain these Kerr classes. So I obtain these walls with Kerr classes T to E1, where E1 is a fiber of the exceptional Kerr locus over the line L1, E2 is a fiber of the exceptional locus over the line L2, and L is the strict transform of a general line. So we described this change of variables from Tij's to Kerr classes in our paper with Mark. So we obtain a consistent scattering diagram which has walls with Kerr classes. And what does it tell us about enumerative geometry, about punctured invariants? So we know that by the description of the canonical scattering diagram due to Gross-Siebert in all dimensions, these walls are of the form H dot is some wall support of the wall. The wall crossing functions are of the form exponential of some constant times some punctured low Gromov Witten invariant t to beta z to minus u. So if I take the log of these wall crossing functions that I obtained purely algorithmically after a change of variables from Tij's to Kerr classes, I take the log of it, I obtain some coefficients, and our algorithm is telling that these coefficients are telling us punctured low Gromov Witten invariants. What kind of punctured low Gromov Witten invariants are they telling us? I have 5 minutes. I apologize, it will be quick. So when you define punctured low Gromov Witten theory, I will tell the enumerative problem these solve. So if you look at an n-dimensional Calabi-Yau variety XD, the expected dimension of the moduli space of punctured log maps of genus 0 with one punctured point, with only one punctured point with a given contact data with the toric boundary, this dimension of this moduli space is dimension x minus 2. And if you also fix the combinatorial type of a log map, which I mentioned at the beginning, by definition of the basic monoids, not very trivial, it follows that in good cases, if the moduli space is log smooth, the dual of the basic monoid is exactly the same dimension as the codimension of the strata corresponding to tau in this moduli space. So because our moduli space is of dimension n-2, the strata of this moduli space, we want to count zero-dimensional strata in this moduli space. So we need to count things with basic monoids being of dimension n-2. And that's what we do. We look at punctured log maps with only one contact order with the boundary where the basic monoid is of dimension n-2. And I say here what I said here in this slide is in good cases because I assume if the moduli space is log smooth, in general it is not log smooth. And this is where all the subtlety with the art and fun is coming up, which I summarized here in this slide. So what we do is we look at, for instance, because we look at n-2 in dimension 3 one-dimensional basic monoid, we look at log maps whose tropicalizations trace out a one-dimensional family of tropical curves, so they do form the walls. Our walls are of one-dimensional, our walls are formed by tracing out one-dimensional families of curves, which form two-dimensional walls in dimension 3. So as a particular example, we are looking at this, our scattering algorithm told that we have a wall, we need to add a wall, like say in the left-hand corner picture, where the attached wall crossing function is given by 1 plus t to the sum curve plus y plus t to the sum other curve plus xy. So it says that if I take the log, there is a coefficient. This coefficient is exactly the number of punctured log maps who have just one punctured point with the boundary and whose tropicalization traces out this wall. So its tropicalization is a one-dimensional family, and it traces out this wall. So what are these punctured log maps? My last 2 slides. So I want to look at maps of class given by the power of the t. So k times l minus e2 minus l times e1. So if I look at P3 with 2 lines and if I blow up these 2 lines, and if I want to get some curve of this class and P3 blown up at 2 lines, where E1, E2 are classes of fibers of the exceptional locus, I can look at green line L, as I depicted in the figure, such that it lies totally inside P2 and intersects the other line L2 at one point. If I take the strict transform of L, it will be of class L minus E1 minus E2. And I can take a k-fold cover of the strict transform. It will be of class k times L minus E1 minus E2. And what I want to end up is of class k times L minus E1 minus E2 plus k minus L times of class E1. So what I do is I look at the point of intersection of my green line L with my first line L1 that I blow up. It says k inverse images under the k-fold cover, and I attached P1 fibers to k minus L of these k points, and I map them to the exceptional fibers. So I get the correct class, and it amounts to making a choice k minus L, choosing k minus L points among k points. So that's why you have the coefficient k minus L in this case, and this is just the multiple cover formula in higher dimensions. So in particular, in this particular example, we derived the multiple cover formula minus 1 to the k plus 1 over k squared in higher dimensions, which is usually obtained by some localization techniques derived purely algorithmically. And there are other examples that we computed punctured log invariants just by looking at this algorithmic procedure, what the wall crossing functions we obtained are, which are in general too difficult to compute because you might have using usual virtual techniques. I think maybe it's a good point to stop here. I think I shall stop here. Thank you very much for your patience.
All right, well, let's thank Hülya. Are there any questions?
Apologies, I probably lost everyone when I start talking about this log, punctured log. I feel it's very difficult because there's a lot of background material. I haven't found a good way. Apologies, particularly to Dan. Sorry.
A question. So is there a case that is not related to toric variety where things have been computed? Or is everything starting with a toric variety and modifying it?
Yes, that's a very good question. Everything in our paper is starting with a toric variety and blowing up something from the toric variety. And there is yet so far no computation. And it's very good question. In dimension 2, we always had a toric variety, toric model. Here you can blow up in higher dimensions. It's not necessarily the case. maybe in dimension 3 out of 105, I don't know, maybe around 60 of the 3 fauna varieties could be obtained from toric. And we don't know anything on how to compute the other cases yet. Yeah. Maybe there needs to be done something different to be obtain these toric fan-like things or scattering clips. Maybe we need to do some things for the degenerations or some things. We haven't solved that out. We thought about it at some point, but yeah, we haven't done that, and there is no competition.
I gather Gross and Siebert tell you that the punctured invariant will give you something. It's just that you don't know how to compute it.
Exactly, yes. We just don't know how to compute it algorithmically. Yes, Gross and Siebert tell that the punctured invariants will fit into the mirror symmetry, but yes, that's true. We just don't know how to compute these invariants algorithmically. Yes.
Do we have any other questions? All right, well, let's thank Hülya again.
Thank you.
Do you want to stop the recording?